Good evening.
Am I audible? Yeah. Okay. So, do you have any doubts? Which week? Okay. Okay. So, we will be solving some similar problems only today. So, after that, maybe if that clears your doubt. Yeah. Yeah. Sure. O- Okay. Uh, so, where are you teaching right now? Okay. Okay. So, that's great. I'm still a student, so don't call me like that. So, yeah, we can start in maybe 2, 3 minutes and then, yeah. Hello. Hello. Can someone confirm if I'm audible?
Sir, you are audible.
Okay. So we can start this week 8th session. So I am Anand Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving similar problems that is associated to week 8 assignment for the course Digital Electronic Circuits, which is taught by Professor Gautam Saab from IIT Kharagpur. And let's go to the course outline. So till now we have covered the content till week 7. That is, we have already covered the combinational part in the first 6 weeks, and we have started the sequential part in the last week. In that week, we have covered all the basic flip-flop circuits, that is SRD, JKT, etc. And after that, we have also studied about the conversion of different flip-flops. And at the last, we did some problems related to some of the flip-flop problems only, in which we have dealt with several Boolean algebra and conceptual problems. So in this week, what we'll be studying is we'll be studying different types of register. That is, they are the memory blocks in which we have several cascade flip-flops in cascade, and they are used as a memory block to save certain kind of memory, etc. And then we'll be covering some of the applications, and ultimately we'll go to counters, that is ring counter, Johnson counter, etc. And we'll also cover the topics of serial adder and LFSR, that is linear feedback shift register, in this particular week. So is there any doubt from the previous week? Anyone having any doubts, or else we can start? Okay, fine. So then we can start with the first question of this particular week. So here is a question. It says let the initial state of a ring counter. So it has a statement or a word, that is ring counter associated. Before the clock pulse is applied as 1010, what will be the output waveform of the counter circuit? So first of all, let me give you certain idea what is a counter. So basically, if we apply certain flip-flops in series, in this case we have applied D flip-flops, and if we just cascade them, and the last output is connected to the input of the first flip-flop, as we already know that Q plus of, or Qn plus 1 of any D is nothing but D itself. So what if we are what is happening here is, let's say this is PQRS. So let's say without, before applying the clock pulse, the states, let's say this is Q0, Q1, Q2, Q3, they are stored as PQRS. And once you apply a clock pulse, so what will happen is this Q1 plus, let's say, will become D, and that D is Q0. So if I write maybe something like this, so after applying the clock pulse, what will happen is this Q1 will become Q0. Why? Because Q1 is D1 and D1 is connected to Q0. This is Q1 plus basically, which has come from the characteristic equation of the D flip-flop. And similarly, this will be now Q1, this will be now Q3, and this Q3 will come as an input to this P. So what we can say, this is, sorry, this will be Q2. So what we can say, this PQR will get shifted, and this S will get shifted at the first place. So that is why this is called as a shift register. The shifting of bits are taking place. So in this particular question, what is asked is, similarly, we have a shift register, that is we have 4D flip-flops, and the output of the last flip-flop is connected to the input of the first flip-flop. So it says the initial state, that is without applying the clock pulse, it is, sorry, it is 1010. So what will be the output waveform of the counter circuit? So it has not specified like what type of, what number of clock pulse it has applied. So we'll do the analysis till we get a certain output or a certain time period. So what I'll write is, I have a 1010 as Q1, Q2, sorry, I guess it is, yeah, it is Q1, Q2, Q3, Q4. Give me a moment. So what will happen? This is without applying any clock pulse. So once I apply a clock pulse, as I explained in the previous slide, so this one will get shifted here, this 0 will get shifted here, and this one will get shifted here, and the last output is the input to the first flip-flop. So what will happen? This 0 will get shifted here. Now if I again apply the clock pulse, what will happen is, it will again do the same thing. This 0 will be shifted here, this one here, this 0 here, and this first one will get shifted here. So you can see you have already reached the first state that was given in the question. So what will happen? It will go from, without applying the clock pulse, it will go from 1010 to 0101, and then again it will repeat itself. So these are the only two states that are possible for the following ring counter. So as we can see in the options, the option says that before the clock pulse it was one. No, I just should write it 1010, and it will go again from 0101 and so on. So this was without applying the clock pulse. So we can clearly eliminate the option C and D because they have some 00 and they have some repeated pattern of 0 and 1. So C and D cannot be the option. So we'll check from A and B only. So the first, sorry, the option B is 101010 like that, and option A is 0101 0 1 0. So you can clearly see after applying the clock pulse what is happening. That is, this is before applying the clock pulse, and after applying the clock pulse we have got this 0 as a pattern. So what will happen is, okay, give me a moment. My slides are still visible, right? Can someone confirm? Yeah, okay, fine. So what is happening is we are getting a 0 1 0 1, and after that we are getting a again repetitive 1 0 1 0. So you can clearly see here, this is the first option in which after applying the clock pulse I'm getting a 0 1 0 1, and then after that it is again getting repeated similarly. So option B cannot be the answer. Why? Because this is before applying the clock pulse, and the question has clearly asked what will be the output of the counter circuit once the clock pulse is applied. That is the pre assumption that we have to make. So for the this question the correct answer should be option A. Is there any doubt in this? This was quite a basic question, I guess. So if you have any doubt you can ask straight away.
Sir, hello.
Yeah, yeah.
Sir, I think if the B waveform B, if it is shifted, that would have been a correct answer.
Yeah, so that is option A only. Like if you shift the B waveform by a single bit, let's say like this, so this is option A. That is why I marked option A as the correct answer.
Okay, okay. Yes, yes. Thank you, sir.
Yeah. Any other doubts? Anyone? Okay, so if there are no doubts, maybe you can try, all of you can try this problem. This is again a similar problem. So it says in the following circuit, consider the initial values to be 0. So in the previous question, what was given is initial value is 1010. So instead of 1010, it is given that we have all the zeros as uh, all the initial states. The output will again be 0 after how many clock cycles? So you need to apply the clock cycles till you will again get this 0 0 0 0. So you will start from 0 0 0 0. So you need to count the number of clock cycles when you are getting the output as 0 0 0 0. So you need to tell me the number that you are getting. So maybe I can give you 5 minutes and let me know what is the answer. And before starting, if you have any doubt, you can ask straight away. Then, or I can wait for 5 minutes. Then, uh, is there any doubt in executing this problem? And one more thing is this is Q4 bar because it is applied at the below. Rest is fine. So maybe you can try it for 2 3 minutes and let me know the answer in the chat box, and then I'll try.
Sir, hello. Hello. Am I audible, sir?
Yeah, yeah. Yes, yes, you are
Sir,
audible.
sir, I think after four clock cycles.
Okay, so I've got one answer as 4. Maybe I'll wait for two
Okay.
minutes more and then I'll solve it, because let's
No
other
problem. No
also give
problem.
some time. Yeah. Okay, so let me start doing it. If anyone get any answer in the between, you can type in the chat box or open your mic and let me know the answer. So we have a 000 as the initial state, and maybe I can write this as already given Q1, Q2, Q3, Q4. So we just need to find the relation for each and every block. So let me write. So this Q1 is nothing but, so we know that Q1 plus will be D1, Q2 plus will be D2. Similarly, Q3 plus will be D3 and Q4 plus will be D4. And we can clearly write the relations for Q4 will be plus will be D4 and D4 is nothing but Q3. Similarly, this will be Q2 because D3 is connected to Q2. Similarly, D2 will be Q1, and for the first relation what we have is D1 is getting XORed. Okay, so we have a Q4 complement here, and this is Q3. So we have Q3 XOR Q4 complement. So these are the relation that we need to apply. So we can clearly see the first three bits will be shipped in a similar fashion as we have done in the previous question. So this will be 0, 0, 0, and the Q1 and what will Q1 be? Q1 is nothing but Q3 XOR Q4 complement. So I'll do that. So this will be 1 XOR 0, that is 1. So if you have any doubts in any of the steps, so you can wait. Sorry, you can stop me and can ask straight away. So I'm now doing, this will be 100. So this is getting shifted right like this, and 0 XOR 1 will be again 1. This is 110. Then again 0 XOR 1 will be 1. This is 111. And then we have 1 XOR 1 will be 0. Then we have 011. 1 XOR 0 will be 1. Then we have 101. 1 XOR 0 will be 1. Then we have 110, and 0 XOR 0 will be 0. So I'll write the further steps here. 0110 is again repeated. So this will be 011. 1 XOR 1 will be 0. So this will be 001. 1 XOR 0 will be 1. 100. This will be 0 0 10. This will be 1 101. This will be 0 0 10. This will be 0 0 1. This will be 0 0 0 0. This will be 0. So 4 is clearly not the answer, I guess. Let me check how many clock cycles I took. So this is the first, this is the second, third, fourth, fifth, sixth, seventh, eighth, 9, 10, 11, 12,
16,
13,
16,
14, 15.
15.
So yeah, so the answer will be after 15 clock pulses, you will get the output 0000 again. So is there any doubt how I have written all these steps? Anyone having any doubts? I have in each and every step I have done the shifting of these three bits, and the first bit is getting calculated by the XOR of this particular expression. So the correct answer to this problem will be 15. So 4 is not correct. Yeah. Any doubts? Okay, the initial part means this particular expression. So, okay, so let me repeat the whole problem. So initially what is given is Q1, Q2, Q3, Q4 all are 0 because it is given in the question. So you need to apply the clock pulses till you will get this 0000 again. So the initial part, so this is nothing but again a ring counter or a shift register because the bits are getting shifted. So what you can say is for each and every clock pulse, you will get a certain Qn plus 1. So let's say for Q4, Q4 plus will be D using the characteristic equation D4, and D4 is nothing but connected to Q3. Similarly, Q3 plus will be, let me use some different thing. Q3 plus will be D3, and D3 is, you can clearly see it is connected to Q2. Then Q2 plus will be D2, which is connected to Q1. So we can clearly see that these three bits are getting shifted to one place because Q4 has become Q3, Q3 has become Q2, and Q2 has become Q1. Now for the last bit, that is Q4 or Q1 plus, it will be D1. And you can clearly see here D1 It is the XOR combination of Q4 complement, which is coming from this, and this is Q3. So here Q3 is getting, and this is connected to this XOR gate. So that is why I have written D1 or Q1 as Q3 XOR Q4 complement. And this is how what I have done now. I have like shifted these three bits to one by one, and Q1 is getting calculated in each and every bit by Q3 XOR Q4 complement. Does it make sense? Is it clear? Okay, okay. So the correct answer is again 15. Okay, so let's go to the next problem now. Okay, so it has this problem is belongs to LFSR, that is one of the topic of this week, that is a linear feedback shift register. So what LFSR is, it is nothing but a basic combination. So because it is a 4-bit question, so I'll give you example of 4-bit only. So LFSR is made using different block diagrams using the polynomial representation. So in this question, what is given is a 4-bit LFSR is given having a combination of x cube plus x square plus 1. So the general denotation is always given by this is the input is x raised to power 0, that is 1. The first block is x raised to power 1, then 2, then 3, and then 4. So whatever is given in the equation, we need to XOR each of the terms. So what we need to do, so let's say in the given question it is x cube and x square. So these are the two terms that are included in the polynomial expression. So what we need to do is we just need to XOR them and connect it to the extra one that is given. So this is the LFSR block representation of the given polynomial equation or the polynomial representation. And the initially it is initialized as 1 1 1 1. So is there any doubt here first of all? Okay, so if you don't have any doubt, so we can proceed. So again, maybe I'll let some of the variables. So let's say this is maybe P, Q, R, S. So P, Q, R, S is initially 1 1 1 1. And what is happening is again these 3 bits will get shifted. So if I write the relation again, this will become PQR, and the first bit that is P, you can clearly see this green, this is nothing but Q XOR R. So now we'll again do the same thing. We'll shift it 1 1 1, then this will be 0 0 1 1, this will be 0. Sorry, let me first see the question. So it says the generate pseudo random sequence has a period. So again, for finding the period, we need to get back to this 1 1 1 1 to check what is the amount of cycles that we are taking to get back to the initial state. So I've done it, so you can also do it side by side. 0 0 1 is getting shifted, again it will be 0 0 0 0, this will be 1, this is 1 0 0, this will be 0. Sorry, I've done something wrong, I guess. This is Q XOR R, right? So this is 0, this should be, yeah. So 1 XOR 1 is 0, that is fine. This is 0, so this will be 1, so this will be 1 0 0, 0 1 0 will be here. This will be 1, then 1 0 1, this is 1, and 1 1, sorry, 1 1 0, this is again 1, 1 1 1 0. Okay, I've got something, fine, fine, fine. So you can see I had a 0 1 1 1 here, and I have got it again. So the initial state will never come again if I like use this circuit. So what it happening is how many clock pulses are getting. So this is the first, second, third, fourth, fifth, sixth, seventh. So in 7 clock pulses, you will get a random sequence or pseudo random sequence of this particular polynomial representation. So the correct answer to this problem is option A. And again, there is a shortcut to do this. For any n bit LFSR, what we do is the period is given by directly 2 raised power n minus 1. So for the given question, n was 4. So period we can directly write as 2 raised power 4 minus 1. It was 4. Yeah. So that should be 15. Okay, give me a moment. I guess 2 raised power. Okay, so I'll clarify this. I guess this is something I'm not sure right now. Is it 3 or 4? I'm not sure if this is n minus 1 or n. So you can just leave it for now, the shortcut part, but this is the conceptual or the most conventional way of doing this. So we are getting the clock pulses repeated after 7 pulses. Is there any doubt in the way that I have done? Okay. So let's proceed then quickly. Okay, so we have this question. Okay, so this is a good question. So maybe if you want to give it a try, you can give it for 2 minutes or 3 minutes and then I'll solve it. This is a very good question, I guess, to solve. Uh, if you got any answer, you can let me know in 2 3 minutes. Otherwise, I'll solve it. Okay, so maybe I can try it out if you are not getting any answer. So the question says that determine the inputs of the JK flip flop, that is J and K here. We need to determine this J in and K in that is given in the question so that the circuit below functions as a n bit serial ladder. So this is nothing but a full ladder circuit in which we already know the sum is A XOR B XOR C, that is a carry, and the carry is nothing but AB plus BC plus AC. I hope it is already you are already aware of this. So this is the next state of the JK flip flop, that is Qn plus 1. So somehow this is a problem of flip flop conversion, that is we need to find J and K in terms of the given inputs and output, as you can see. So let's start the question. So in this, the S is given by, you can see X, Y, and then the third is this C out, that is Q n plus 1 only. So I'm writing it, S is given by X XOR Y XOR, what is this? C out. And C out is AB plus BC plus AC in general. So I'm not writing that right now. So now what we'll do is we'll first of all write all the possible combination that can be possible. So maybe I'll write Qn, that is here, then X and Y. So what we'll do is now we'll calculate the sum and carry, that is S and C, that is given in the question. So first of all, I'll write Qn plus 1, that will be C out. And then we have a S. So Qn plus 1 is nothing but the carry of the adder. So I'm doing it. I hope you already know carry is AB plus BC plus CA. So, or you can directly do 0 plus 0 is 0. And then 0 plus 1 is 1. So carry will be 0. Similarly, this will be 0. This will be 1. This will be 1. This will be 1. And this will be 1. Is there any doubt in writing this C out?
No, sir.
Okay. So now I'll write the sum. Sum is again, I'm writing it directly. So 0, this will be 1, 1. This will be 0 because it will be 10. Yeah. Then this will be 1, 0, 0. This will be 1. So now what we have is we have a Qn and we have a Qn plus 1. So we need to find just J and K on the basis of this, and then we'll clearly get the relations of X and Y in terms of J and K. So for that, we already know in the previous lecture I taught how to make or how to do the flip-flop conversion. So for that, we need the excitation table of the available flip-flop, and then we'll write the Boolean expression of the available, that is XY. So I'll just make the excitation table quickly. So to repeat again how to make the excitation table, I'm doing it again. So this is JKQN. This is the characteristic table. This is, I'm doing it a bit faster. I hope you already know. So Qn plus 1, when J and K both are 0, it remains Qn. When J and K is 0, 1, it will be 0. It will be 1 when J and K are 1, 0. And it will toggle. So this is how what we do is we make the, sorry, excitation table now quickly. So there can be 4 cases, that is 0, 0, 0, 1, 1, 0, and 1, 1. So when Qn are 0, 0, it is this and this case. Sorry, this will be 0, 0 here and here. So it is 0 and x. Similarly, when we have a 0, 1, that is here and here, it will be 1x. Then we have 1, 0. So 1, 0 is here. And where is else is 1, 0? Here. So we have a x1. And finally, we have two 1, 1s in which we have a x0. So I hope you are already aware of this characteristic table. So using this, we'll now fill out the previous table, that is this J and K. So whenever it is 0, 0, okay, so in all these three cases, it is 0, 0. So we have 0x. I hope it is clear. If there is any doubt, you can ask straight away. So when we have a 0, 1, it is 1x. When we have a 1, 0, it is x. What was that? It was x1. 1, 1 is x0. 1, 1 is again x0. Again 1, 1 is x0. So is there any doubt till here in this problem? Fine. So we'll proceed now using a K-map. We can quickly write the relations. So we'll make the K-map out of it. So I have written Qn plus, so it will be Qn bar Qn. So I'll fill it. For J it is 0, 0, 0, 1, x, 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 x. So 0, 0, 0, 1. And for K, let me use some different things. So for K it will be x 1. Okay, so x, 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 1, 0, 0, 0. Hmm. So for J, you can clearly see there is only a single pair possible, that is this. So J will be x, y. And for K also, this is the only pair that is available. So K will be x complement, y complement. Okay, so is there any option like that? Yeah, option A is still, sorry, option A is directly the answer. So is there any doubt? This was a very good question, I guess. So if there is any doubt, you can ask straight away. And this is how we have done it. Any doubts, anyone? Any doubts? Okay, we can move forward then. Okay, so the given question says a 8-bit serial in parallel out. So serial in parallel out is a kind of a register in which we give the input serially and take the outputs parallelly, is used with a clock frequency of 2 megahertz. Considering the initial register is all of them are 0. So I've already got one answer. Let's see. The time required to transmit the 8-bit value to the output is. So this is a very straightforward question. So basically the given question says it has a frequency of 2 megahertz and the time period will be 1 by f and the number of bits that needs to be shifted. So this is a very straightforward question. You don't need to do any analysis here. So let's calculate it directly. So 1 by 2 megahertz times it is a 8-bit. So it will be 4 microseconds. Option C is the correct answer. Any doubts here? Anyone having any doubt?
No, sir.
Okay, fine. So we quickly we can proceed. Yeah, so this is the question now you can do. So this is a counter which is given, which is named as Johnson counter. So we'll see what it is. It is a clock diagram is given that is having a time period of 1 milliseconds. So initially it is given as 0000 and the delay is 1 millisecond. So after how much time the counter will be 0 again. So first basically you need to count the number of states and that is how you will get the relation. So maybe you can take 5 minutes and let me know the answer to this question.
Hello, sir.
Yeah.
15 milliseconds. 1 5.
Okay, so I'll check maybe in a minute.
Okay.
Okay, so let me try to solve it. So it is a Johnson counter, it is saying. So it is a special kind of counter in which the last state, that is the first state, is get equal to the complement of the last state. So let's try it. So we have, let's say, q1, q2, q3, q4. So the first state is equivalent to q4 complement, and initially it is given as 0 0 0 0. So I'll solve it out. So this will be 0 0 0 and 0 XOR 0. Oh, sorry, 0 XOR, this will be q4. This is 1 0 0. This will be 1 1 1 0. This will be 1 1 1 1. This will be 1 1 1 1. This will be 0 0 1 1. What is this? This will be 0. Then it is, sorry, 0 0 1. This will be 0. And finally, I have a 0 0 0. Maybe I can use a new page fit. Then I have 0 0 0, and this will be 0. So I have already got this 0 0 0 back at this stage. So now the question says the initial state was 0 0 0 0. Consider a delay from input to output of each flip flop. So input to output, we have a delay of 1 milliseconds for each and every clock pulse. So after how much time of the output of the counter will be 0 again. So this is 1, then 2, then 3, then 4, 5, then 6, then 7, and then, okay, so it is already, so will not count it the first cycle, because what we need, yeah, yeah, sorry. So 1 2 3 4 5 6 7, and then we have a 8. I guess 8 is yeah, so 8 will be the answer. So why someone said 15, I guess. So is it clear why it will be 8?
Yes, yes, clear, sir.
Okay. So output will be 0 again, since the delay for every clock is 1 millisecond. So output will be 0 again after 8 milliseconds, because so, or you can do it directly also. So for any n bit Johnson counter, we have 2n output states or 2n states possible. So you can see there are 8 states possible for a 4-bit Johnson counter. That is what I was meaning. So 8 state means 8 millisecond directly. So you can do it by looking only the particular question. So is it clear to everyone? Okay, so you can all try out. Maybe try to do it in a bit quicker. So let's say I'll increase some of the options. Maybe D as option 2, and multiple choice question. Let's say multiple answers can be correct. This is a similar question as previously. So it is a 4-bit Johnson counter, which is initialized by a sequence of 1 1 1 1. Which of the following values converted to decimal will not occur in the counting states? It is will not. Please emphasize on this and let me know the answer. Maybe in 2 3 minutes, and then I'll solve it. Yeah, hello. Any
Uh,
doubts?
sir, I think it is 5, B.
So I have said the multiple answers can be correct. So kindly take a look at it quickly.
5 and 2. 5 and B and D.
So I've got one answer. So okay, I've got
B
two.
and B and
Fine.
D.
Yeah, yeah, okay, fine. So let me check now.
Okay.
So it is a 4-bit Johnson counter, so I'll do it quickly. Sorry. So this will be 1 1 1, this will be 0, this will be 0 1 1, this will be 0. Okay. So these are all the possible states that are available. So I'll write in decimal. This is 15. This is 7. This is then 3. Then this is 1. This is 0. This is what is this? This is 8. This is 12. This is 14, and again it will be 15. So it will be 1 3. Sorry, 1 3. I have not done anything wrong. 1 3. And what I have is 7 8. I had a 0 also. 12 14 15. So I have a 3 also, I have a 7 also. So yeah, 5 and 2 are not possible, so B and D will be the correct answer. Yes. Any doubts here?
No, sir.
So similarly, you can do it for a 3-bit Johnson counter also. So let me do it quickly so that you should already be knowing that what are the possible states. So it will be 0 0. Sorry. All the possible states are 0 1 4 6 and 7. So you need to remember this that all for the 3-bit Johnson counter, I have sorry, wait. So this will be 0 0. This will be when I've drawn not written it correctly. Let me. This will be 1 0. This will be 1 1 1. This will be 1 1 1. This will be 0. 0 1. This will be 0. Yeah. So the possible states are 0. Then I have a 1. This is 0. This is 1. Then I have 3 also. Then I have a 4. Then I have a 6 and 7. So again, for an n bit, I already told you n bit counter, I have 2n states. So you can see for 3-bit, I have total 6 states. So you should be aware that 2 and 5 are not available in the Johnson counter for 3-bit, and similarly for 4-bit, you can check by yourself that what are the not available states. So the total states are 8 here for a 4-bit counter. Is it clear to everyone? Okay, I hope it is clear. So okay, so let's move forward. So the question says which of these two LFSR circuits can generate the maximum length sequence? Okay. So maximum length sequence is nothing but it can be represented in a polynomial representation. First of all, if we have a n-bit LFSR, so the maximum length sequence is given by, it can be represented in two ways. First is xn x plus 1, and the second is xn minus n plus xn minus 0 and x, sorry, I've written it, this will be 1 and this is xn minus 0. So if the given expression for any n bit follows these two polynomial, then it is a maximum length sequence. So we can use these to get the answer quickly, I guess. So it is both of them are 4-bit first of all. So for 4-bit, a maximum sequence can be. So I'm writing 4 here in the given above expression that I have. So this will be x4 minus 4 plus x4 minus 1, and this is x4 minus 0. So this will be x4 plus x3 plus 1. So we have two given possible maximum length sequence, that is x4 plus x plus 1 and x4 plus x3 plus 1. So now let's get to the circuit here. So I have already told, so this is x raised to power 0, this is x1, x2, x3, x4, and this is again similarly. So the XOR is getting here x3 and x4. So this will be given by 1 plus x3 plus x, uh, what is this, 4. And this circuit 2 will have a sequence of, this is x1, 2, 3, 4. So this has 4 and 1 XORed. So 1 plus x plus x4. So is there any doubt till now how I have written these polynomial expressions? Okay, so we can check whatever the maximum. So one is x4 plus x plus 1, which is this. Circuit 2 can give a maximum length sequence. Then the second is x4 plus x3 plus 1, yeah, which is this. So both of the circuit can generate this maximum length sequence. So the answer to this question will be option D. I hope it is clear. Any doubts?
Sir, how are you deciding it's both are same?
Both are same meaning.
Like both give maximum length.
So what is the question exactly?
Which of these, which one we can find, which one will give maximum length?
Both of them can give. That is what I said. So there can be two representation for any maximum length sequence. One is this xn plus x plus 1, and then the second is this. So first of all, I have calculated that what two possible combination can give the maximum length sequence, and then I have checked the circuits.
Okay, sir.
Yeah. So is it clear to everyone? Any doubts here? So I hope it is clear. So let's move forward. Okay, so maybe you can try this out. This is a 4-bit LFSR with an external feedback, has a polynomial representation of this. Okay, I think it is repeated, or have you already done this question? I think it is kind of repeated. So maybe you can give it a go and let me know the answers, since now you know how to do it. You can take 2 minutes and let me know the answer quickly. So I've got a 7. I guess we have done this. So let me do it quickly. So this is 1, 2, 3, 4. So 2 and what is this? 2 and 3 are XORed. So this will be, yeah. So this will be the combination. So let's say I start with 0, 0, 0, 0. So it will be 0, 0, 0, and I guess the middle two are getting XORed. So I'm writing it directly. Okay, so I can't start with the 0, 0, 0, 0 because otherwise it will stuck. 1, 1, 1, this will be 0, 0, 1, 1, this will be 0, 0, 0, 1, this will be 1, 1, 0, 0, this will be 0, 0, 1, 0, this will be 1, 1, 0, 1, this will be 1, 0, this will be 1, 1, 1, 1, this will be 0. Okay, I've got the relation again. Yeah, so I guess we have done it. So this is 1, 2, 3, 4, 5, 6, 7. Yeah, 7 will be the correct answer. We have already done this question previously also. So I hope it is clear, right, everyone? Yeah, fine. So, okay. So, proceeding to the next question, it says a delay line circuit. So, a delay line circuit is also a ring oscillator, in which what we have is we have a cascade of n NOT gates which are odd. So, a delay line circuit is to be generated to create a delay of, so it says the delay is given by 0.464 milliseconds between input and output. How many number of flip flops are required? So these are the flip flops in simple language we need to get to produce the required delay. So the clock frequency is given as 1.25 megahertz. So this is a simple relations that you need to learn. So f is given by 1 by 2 n tau pt. So for n should be odd. I mean, for a ring oscillator it should be odd, but for a delay circuit you can do it as even also. But there are two types of circuits. So again, I'm clarifying. Please pay attention. For a ring oscillator, n should be odd, and for any delay circuit, n can be even also. So let's calculate. Maybe you can do the calculation. Let me know what you are getting. So frequency is 1.25 megahertz. Then I have a 1 by 2 times n, and delay is 0.64 milliseconds. So n will be 1 by this will be 2.5 times 0.64 times 10 to the power 3. Okay, this will be 10 to the power minus 3, so it will be 1000 divided by 2.5, and this is 0.64. So uh, let's say this is 25. This will be 8, 8, 8, 5. So maybe 8, 6. I've done some wrong calculations, I guess. 0.25 is 2.5, 2.5 times 0.64. Okay, so let me see any answer that you've got. 1.25 micro you are getting. So we need to calculate n. It can't be in micro, it should be a finite number. So let me redo the calculations if I've done something wrong. 2 times 1.25 times 10 to the power 6 times 0.4 10 to the power minus 3. So it will be 1000. Okay, so it will be 1000, and 2.5 was there. So written an extra 0, 400, and this is 20, 88, 85, 5000, and this will be 8, 6, 48. This will be 22, 625 I'm getting. Are you also getting the same? Can someone confirm? Mm. Can someone please confirm? Let me do the calculation. 1.25 times 0.6. So maybe we can come it back at the moment. I guess 625 is the answer that I'm getting, but there is no option. Maybe we can recalculate it later. So give me a moment. You can also confirm if you're getting the same answer. Till then, we can move forward. Okay, so this is, so it says in the following diagram, register A and register B with loaded with, is this the flip-floppers? After the 8 floppers, what will be the loaded sequence? Okay. So again, this is a very good question. So the flip-flop is initially reset. So this is nothing but there are two register A and register B, that are the memory blocks. They can be anything. They can be made using any flip-flops, and they were loaded with initially. It is given that A is loaded with 0 0 0 0 1 0 0 1 0 0 1, and this is 0 0 0 1. So it is serial out. So it is getting input to the full adder circuit, and you can see this is a toggle flip-flop. That is T flip-flop is given, in which we know that if Qn is 0, then Qn plus is T only, or Qn only, and if Qn is 1, then Qn plus is Qn complement. It is toggle. So let me try to do the calculations here. So it has a full adder, that is, it is getting AI as the input of register A, and then BI is the input of register B. So first, in the first case, 1 and 1 will be input, then in the second case 0 and 0. So I need to write it in a reverse order. So I'm writing it AI BIR 1 0 0 1 0 0 0 0, and BI is 1 0 0 0 0 0 1. Then we have, for a full adder, we have a CI minus 1, that is CI. I will write directly. Sorry, that is nothing but Q connected to Q. You can clearly see here. So, and then what we have is, we need to find the sum and carry. So we just need to find this CI minus 1 to get the correct relation. So let's do it one by one. So initially what we have is, okay, we need to get the initial part. The flip-flop was initially reset. So initially the Q was 0, so I'm writing it here. Now I'm doing the sum and carry of this. So this will be 1 plus 1. So it will be 0 and 1. And you can clearly see this CI is connected to this toggle flip-flop. So again, I'm repeating, if Qn will be 0, this Qn plus 1 will be Qn. If Qn will be 1, then it will be toggle. So once this T gets 1, the Q will get to Q bar, and if T is 0, the Q will remain the same. So since what is there? So since this is 1, this will get toggle. Now I'm doing the second. So again the sum, and this will be 0. So now since this is 0, so what will happen is, okay, I've done something wrong. This CI minus 1 will toggle if T is, Q will be 1. Okay, my bad. So again, you need to check it clearly. If CI will be this T, then it Q plus will be toggling. Otherwise, CI minus 1 will remain the same. So what is happening is, this CI will come here now. Since Q was 0 only, this CI will come here. So I've written it wrong now. Sum will be 1 and CI will be 0. Again, so the Q was 1, so it will toggle, and 0 0 1, it will be 1, will be 0. Is there any doubt till now? If this is clear, then it will be fine. Is this clear, the steps that I have done till now? Yes, I'll repeat. So I have a C minus 1 as a third input, which is nothing but Q only, and I have this CI as an input in T. So this is nothing but T, let's say. So the input is coming from this side, so this will be Q plus. So we need to check this to check what how T flip flop will work. So we need to check this column to check how T flip flop will work. So in the initially the flip flop was reset, so I've written this as 0. So sum and carry we can calculate quickly. So sum will be 1 plus 1 plus 0. So sum will be 0 and carry will be 1. So now you see, since the previous state was 0 only, this will not toggle. This will come directly to 1 because here. So Q will remain same since the previous state was 0. So I have written now 1. So 0, 0, 1 will have a sum and carry of 1 and 0. And now you can see the previously Q was 1. So this Ci will get toggle and this will be 1 now. And 0, 0, 1 will have a sum of 1 and 0. Is it clear till now? Okay. So similarly now again this is 1, so it will toggle the last state, and this will be 1, 0, 1 will have 0 as sum and 1. Again we had a 1, so it will toggle. So 0, 1, 0 will have a sum of 1 uh, and a carry of 0. So now we had a 0, so it will remain same. So it will be 0, 0. Again we had a 0, so it will remain same. We have a 0, 0. Again we have a 0, so now the sum and carry will be, sum will be 1 and carry will be 0. So is there any doubt in this table? Anyone? Please ask straight away if there is any doubt. Is it clear to everyone? Please confirm if it is clear to everyone, or should I repeat once? Please respond, guys.
Fine, sir. Clear.
Okay. So now what is the question? After the 8 clock pulse, what will be the loaded sequence in register A? Okay, so after 8 clock pulses, what will be the sequence? So in register A, we have, what we have done is we have inputted the SI. So we need to check what will be the SI. So first this will get inputted. So I again need to do it in the reverse order because this will get entered in the SI, this register A first, and it will go one by one. So if I write this in the upward order, this will be 1 0 0 1 0 1 1 0. So this will be SI and this will get stored in the register A. Let me check, is there any option like that? 1 0 0 1 0 1 1 0 1 0. Yeah, option B is the correct answer. Is it clear why I have chosen SI as the answer? And that too in the reverse order. Is it clear, everyone?
Yes, sir.
Okay, so let's move ahead now. Okay, so maybe you can give it a try to this problem. It has a ring oscillator as well as two flip-flop also. So maybe you can give it a try in 2 minutes and let me know the answer that you are getting. Any answer? So let me try it out. So we had this ring oscillator in the initial state. So it says in the following circuit diagram, the output signal frequency is 10 kilohertz. So we have a f out of 10 kilohertz. Sorry, the desired output frequency is 10 kilohertz. How many numbers of inverters here? Here it will be f out, I guess. Are to be cascaded to achieve the desired specification, provided the propagation delay of each inverter is 5 nanoseconds. So we already know that any flip flop. I have already told in the last class that if I have a frequency f here, it will be f by 2 here, it will be f by 4 here. So I hope you already attended the last class and already know that this is the case. So you can clearly see here f out will get reduced by 10 by 4, that is 2.5 kilohertz. And in the previous question, I have already told the formula, that is what was the formula? F is nothing but 1 by 2 and tau PD. So we just need to calculate n again. So this will be 1 by 2 times propagation delay is 5 nanoseconds, frequency is 2.5 kilohertz. So this will be 1 by, okay, this will be 10 raised per 6, then again 10, so that raised per 5, then 2.5. So this will be 10 raised per 6, 100 into 10 raised per 4 by 25, so this will be 440,000. Okay, I'm doing it. Let me check. 10 is fn by 4. 4 times 4 then we have extra 4. Okay, let me again check what I've done wrong here. Okay. So we need it 10 kilowatts, so it will be not 10. So if there is 10 here, there will be 20 here, and there will be 40 here. So instead of dividing it by 4, I need to multiply it. Sorry. So do you understand this? What I've done wrong? This will be 40 kilowatts. Let's say this is F out. First of all, do you understand why it is 40 kilowatts? Everyone? The desired output frequency is 10 kilowatts, so we need to do the flip flop, yeah, frequency. So 40 kilowatts I need to write here, not 2.5. So redo the calculation. So what are the answer that you are getting? Can you check and let me know? So this is 10 over 6, so it will be something by 4. This is 10, this is 10 is per 4, this is 10 is per 5, 10 is per 4. So it will be 100 into 100 by 4, so this will be 25. So the answer will be 2500. So yeah, so option, so again I have let you know that the ring oscillator, we have a odd number of sequences, so the correct answer will be 2499. To generate this ring oscillator circuit, we need to have odd numbers, so that is why it is also saying approximate number of inverters. So the answer will be 2499, that is nearest to 2500 also. Is it clear, everyone? So
Sir, please repeat
okay, I should
how
repeat.
we are getting 40.
40, yeah, okay, fine, I'll repeat. So just see this part of the circuit. The question says that the output desired frequency is 10 kilohertz. So in the previous class, I already told that any flip flop, the frequency is getting halved at each and every clock pulse applied. So there are two number of clocks, two number of flip flops here. So at if the output frequency is 10 kilohertz here, I need to have a frequency of 20 kilohertz here, because it will do a flip flop or the frequency conversion of f by 2. It will also do the frequency conversion of f by 2. So if I have a 20 kilohertz here, so I need to have a frequency of 40 kilohertz here. And then we had a frequency of 40 kilohertz at this inverter circuit. So that is why I've used this 40. That is the 4 times of 10 kilohertz.
Okay, sir.
Okay. So let's do this. So we have a 8-bit Johnson counter, which is initialized with the sequence of this. Okay, so 00000000. In the decimal representation, what is the mean value of its counting state? So we have a 8-bit, so we should have a 16 states. Okay. So let's try it out because it will take some time. So to write the decimal representation and then calculate the mean. So I'm doing it quickly. I'm trying it. So you can also try it side by side and let me know the answer. So this will be 100. So, one, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11, 12, 14, 15. I guess I've done it correctly. Then so I hope I've done it correctly. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 6, 7, and 8. Yeah, these are the 16 states. So what we need to calculate is what is the mean value of the counting states. So first of all, we need to do the decimal conversion. So this is 0. This is 0, 1, 2, 3, 4, 5, 6, 7. 2 raised to power 7 is 128. This is 128 plus 64. That is 192. Yeah. Then 192 plus 32 is 94. 194. 224. So quickly let me know all these values. I'm also trying. Plus 16 is plus 8 is 248, plus 4 is 252, plus 2 is 254, plus 1 is 255. Then this is nothing but 128 minus 1, that is 127. This is 63. This is 31. This is 15. This is 7. This is 3, and this is 1. So quickly let me know what is the sum of all these terms. To calculate the mean, we need to do the sum and divide it by the number square, that is 16. So quickly let me know the sum that you are getting. Use your calculators if you have. Let me also try to calculate it. 128. Okay, so is it the final answer or the sum? It must be the final answer, I guess. Okay, so I'm getting the sum as 2040. I'm not sure if this is correct. Please verify if this sum is correct. So 2040 divided by the number square, that is 16, is 127.5, which is option C. Okay, so is there any doubt? Is it clear, everyone? Please confirm everyone if it is clear, or do I need to repeat?
Clear, sir.
Fine then, yeah. Let's proceed. Okay, so this is again a question from CL, and okay, so this is again a serial input parallel output shift register. So it says what is the output? Sorry. Yeah, so what is the output after two clock pulses for a bit sequence of 1 1 0 1 serially entered into a 4-bit parallel out shift register? So okay, so we have serially entered 1101 into a 4-bit parallel out shift register. So give some attention here, which is initially clear. So if we have a parallel out shift register, so what is happening in SIPO is one by one bits are getting shifted. So this happens in a single clock, and in a serial, the serial input will get at the first place. So this is happening in a single clock, and this is happening in that particular clock cycle. Is it clear? The serial input parallel out combination. All the okay. So I've already got one of the answers. So let's see if it is correct. So is the concept clear? First of all, everyone. The parallel out will shift all the bits in a single clock, and this serial input will take each and every clock pulse to do this insertion of this 1101. Is this particular thing clear to everyone? Please confirm it is clear if it is clear. Yeah. So I'm getting different answer. One is 1010 and other is 0100. So let's see. So I'm assuming that this is clear. So in the next pulse, what will happen? This 100 will get shifted, and this 0 will come here. Then in the next pulse, 010 will be shifted, and this 1 will come here, this one. And in the last pulse, 101 will be here, and this 1 will get shifted here. So this is the first, sorry, after first, this is after second, this is third, and this is fourth. So now the question is asked, what is the output after two clock pulses? Okay, after two clock pulses, this is 0100. Okay, so what is the answer? Yeah, so I hope it is clear. 1010 will not be the answer. It will be 0100 after two clock pulses. So option 4 is correct. Is the concept clear to everyone? Everyone, please try to respond. Is it clear? Okay, fine. Then you can try this out. This is again a similar question, and let me know the answer. You can take 2 minutes. Okay, so I've already got an answer as you. So let me try. What is this? Okay, so initially it is 1111, and the data that need to be applied is 1010. So in the first clock, it will be this 0 will come here, and then 011, this 1 will come here, then 101, this 0 will come here, then 010, this 1 will come here. So what is the question? After three clock cycles, so in the first it is this, second, and then this is third. So 0101 will be the answer. There is the, yeah. So all of you are correct. 0101 will be the answer. So option 2 is correct. So is it clear to everyone? Please respond. I hope everyone uh, is able to understand the same. Please respond if this is clear, everyone. Okay.
Yes, sir.
Okay, okay. So maybe we can try this out. This is again a similar question, and let me know the answer quickly. It has a certain relation, so just let me know the answer. So what one answer is 1101. So maybe I'll wait for 1 minute to for everyone if that is fine. Yeah. So after 1 minute I'll solve this. Okay, so now I've got 1101. Okay, fine. So let me solve it now. So initially it is 1100. It says after 4 clock pulses have applied. Okay. So it will be 110, and here it is the XNOR gate. So these two are getting XNOR. So these two particular bits. So 0 XNOR 0 is 1. XNOR is 0, 0, 1, 1. So 1 is 1, 1, 0, 1. 1 XNOR 1 is 1. So this is first, second, third, and fourth. So 1101. 2 will be the correct answer. I hope you have also written the same. Yeah. So 1101 will be the answer. Is it clear to everyone?
Yes, sir.
Okay, so let's proceed. Okay, so this is a theoretical question. It says a shift register with the complement Q complement at the last state connected to the D input. So we have already done this. It is saying that the last flip flop when the Q complement is connected to the first state, what is the counter called? So this is we have just completed. This is a Johnson counter, and it is also called as twisted ring counter. So this is just a theoretical based question. So option 1 will be correct here. So is there any doubt in the questions that we have done in the whole lecture? Since we have done, I guess, a lot of questions, so we can wrap up quickly for today. So we have covered almost each and every topic that is given in the course outline for week 8. So we've covered all the applications also, all the counters also, and LFSR also. So in the subsequent week, we'll be now covering the up and down counters, which are asynchronous basically, and synchronous also, and some of the counter designs. So yeah, I guess for this week, the number of questions are sufficient. So if you have any doubt, you can let me know quickly, else we'll just wrap up the session for today.
Sir, hello, sir.
Hello.
Uh, sir, can you elaborate on population standard deviation regarding Johnson counter?
Sorry, what
What is
population
population standard deviation?
Standard deviation. Okay, standard deviation basically. Okay, so you need to have a good grasp of statistics here. So we have done one question, I guess, which in which I need to calculate the mean. Some question was there. I don't remember. Yeah, so this was the question in which we calculated the mean for a 8-bit Johnson counter. So similarly, there are two more terms, that is standard deviation and variance, which have certain formulas. So you just need to apply those formulas to calculate the standard deviation or the, I guess you have asked for standard deviation, right?
Yeah.
Yeah, so similarly, the way we have calculated mean, you need to calculate the standard deviation also.
Okay.
Yeah,
Thank you, sir. Thank you.
yeah, no problem. Any other doubts? Anyone having any other doubts? If not, then we can wrap up the session for today. We will meet at the same time in the next week. Thank you everyone for joining the session.
Thank you, sir.